of your presentation. And you are also from this M and S decision, right? Yes, it's written here, M and S. Okay, M and S decisions, yes. So, and the title of presentation is Reticular Network as the Lymph Nodes Railroad System, T-cells Migration Modeling by the Free Energy Minimization Technique. Very exciting topic. So please, Ivana, you can start your presentation.
Thank you, Vitaly Isaacovich. Good afternoon, dear colleagues. And let me share with you with the results of my last scientific work. And before this, I would remember that it's not the first time when I talk at in the seminars or conferences under this name of mathematical modeling in biomedicine, because almost 5 years ago I participated at the conference Mathematical Modeling in Biomedicine in Rudan University. And if you not in the full screen mode, you can see the program of this conference. And there was also my report, but about other things. And also this conference was very interesting presentation. I'm not sure what was the authors of this conference. Someone from Czech, I suppose. Maybe it was Kazmirchak, Daletsky, and Lipnyatsky. Polarization on concave domains by traveling wave pinning. And it was very nice, elegant work. Now I would call it some minimal model, maybe in partial using partial differential equations to describe in one or equation or two maximum equations the T-cell or cell in general gliding in very similar manner as it is in the nature. And today's work is also about T-cell migration along special structures, fibroblast reticular network. These structures we can observe in lymph nodes, and me and my dear colleagues, my co-authors, prepare some calculations and thoughts about this. First of all, fibroblast reticular network is T-cell railroad system, and it plays a very important role for immune system and especially in lymph nodes. The inner part, the internal part of network plays the role of we can say tubes, and antigens move in these tubes to the dendritic cells. And you can see on the right picture, I will use pointer. Yes. And you can see on this picture how antigens, it's yellow yellow dots, move inside these structures to dendritic cells. Dendritic cell can be anchored on this system and wait for more motile cells like T cells or B cells. And taking this in consideration, considering this, this network is very important for a T cell activation. Because this special rod system can do it, this motion more directional to dendritic cells, and I can repeat that T cell activation is most important process for immune response initiation, because on this stage dendritic cells activate T cells, and the massive cell cognate cell proliferation start from this point. Well, and we should underline this, that the real motion of T cells is superposition of random motion and directed type of motion. And directed type of motion is closely connected with chemokines, which are emitted by dendritic cells and reticular cells, which build this network. And this chemokine gradient can direct already activated T cells to dendritic. Well, in lymph nodes, not only there are not only fibroblast reticular network for T cells. There is also dendritic cells network for B cells, and this is these two types of networks can divide and limit the whole area of lymph node on two areas, and T cells cannot migrate to the B cell follicles, and B cells cannot go to the T cell zone or paracortex. There was also very interesting computational works about T cells motility using fibroblast reticular network. And this work was very useful to reveal possible physiological role of network on T cell motility and density of this network also. Well, this slide is more close to today's main theme of my presentation. We know two main types of eukaryotic cells movement. It is swimming with flagella. We know also that prokaryotes and especially bacteria also can use flagella, but their flagella is built on other physical processes. His flagella is more close to them, for example, corkscrew, like for battle. And other type of eukaryotic cell movement is crawling or sliding, we can say gliding, of cells on some surface or some elongated structures. And today I'm going to describe the second type of motion. What is the key structure element of such motion? I mean, gliding along some elongated structures. We know about cytoskeletal component. It's a lamellopodial based motion using wide front of myosin structures connected with ERP2-3 proteins. It's special structures blabbing built from cell membrane connected with a special myosin core. It's also a cortical flow of myosin fibers in cells, and structures which are very close to the lamellopodial structures. It's finger type structures, filopodial, and it's cytoskeletal elements. And also some researchers reported about other element which is also contributed to the gliding of cells. It's membrane reconstruction also. It can be membrane unfolding model. It can be caterpillar flow model, very interesting model, and more close to the real processes in cells, fountain flow model, when special bubbles, membrane bubbles, initiates in the backside of a cell and then go to the front of the cell. But today I will describe motion based on cytoskeletal structures. What is the goal of the current work? I'm going to reproduce the characteristic sliding movement of lymphocytes along special linear structures of reticular fibers. Well, special characteristic external details should be imitated and reproduced, but internal processes as adhesion or actin polymerization, we do not need to be taken into account. Well, and of course, this model have to reproduce both stochastic and directional type of motion. Types of motion. And on the next slide, you can see the main stages of cell gliding by this cytoskeletal mechanism using actin proteins. First of all, we have a cell with special regions connected with a substrate using other proteins like adherins or integrins. And we know also direction of future motion. On the next stage, the myosin fibers move to the leading edge of cell, and they form new leg, new front part of cell. And then this new region of cell also fix on this substrate, and then occur the adhesion of the trailing edge. You can see that this leg of cell disappear. And on the next third stage, we can repeat the first stage, and as a result, we can see some more or less persistent motion of cell along some substrate surface or fiber or someone else. And let's talk about methods and approaches which can be used for such modeling. One of them I remembered before slides. Such models called minimal models, and this approach is more complex, but of course I'm not sure that it's more that this complexity is very helpful property of method, and very big amount of methods. But let's see the short view of such methods. We know different scales of modeling, cellular scale or micro scale. When we can use ODE or Boolean networks approaches to describe intracellular processes, reactions, some cascade mechanisms. We also can view a cell and describe cell and first of all between cell processes on mesoscale level using very wide spectrum of approaches. And on the macro scale, you can use ordinary differential equations such as pK, pharmacokinetic equations to describe, for example, drug movement, or it can be some other sorts of therapy, like not drug, but for example, cell therapy distribution in our body between different tissues and organs. And on mesoscale, and today we will talk about mesoscale level of description of immune system description. Which approaches, which method can be used on mesoscale? Sorry me for these captions on Russian. I have not enough time to correct them, but I will of course translate when I will talk about the slide. Yes, we already discussed that on micro level, you can use ordinary differential equations, and it will be some type of continuous methods. You also can use partial differential equation to describe concentration of some chemokines, cytokines, or even cell concentration in, I will repeat, in partial differential equations. But also you we all have other approaches, discrete approaches, which can be on lattice and off lattice. And we have very rich variety of approaches, more or less complex. For example, it is very complex immersed cell boundary approach with large amount of cell details, and on other level with very big spatial scale, you have such approaches like multi-compartmental cellular automata, when on one compartment or one method cell, not biological but method scale, you have several biologic cells. And as on lattice approaches, you have also very well known as precursor of other approaches, cellular automata, cellular pods model, and off lattice approaches. You have such interesting approaches like vertex models without any lattice. You have also well known in mathematics Voronoi diagrams, and widely used in engineering and technique areas, finite elements approaches for cell and tissue description. You have also very interesting modern approach like phase field theory. I mean special auxiliary field to describe cell motion, and use partial differential equations to describe such motion. And if you talk about these approaches which can describe cells by individual based approaches, to describe cell motion along reticular fiber network, we should use such approaches which can effectively describe and imitate cellular motility. There are two approaches which can describe cellular motion in very effective manner, and as cellular pods model using different techniques, different ways to describe such cell motion. Well, briefly, in two. Sorry.
No, there are no questions. You can continue.
Thank you. In several slides, I tried to describe this approach, solar post-modeling approach, which I used to describe to imitate motion, the T-cell migration along reticular fibers. It's on lattice models, and on this picture you can see these elementary sites on nodes, and the all amount of sites which have the same spin variable, the all sites, I repeat, that have the same, for example, red spin, it's one biologic cell. And a little bit lower, we have, for example, 20 sites, of course, connected sites, which can which we can call the green cell. And also here we can see the medium size. In each model, you also can describe some, for example, extracellular matrix. And to describe different forms of cellular behavior, you can use special structures like from theoretical mechanics and or statistical physics, like Hamiltonians. Is effective terms of energy, and it's not the full possible forms of energy of cell energy. It's only some types which we need to imitate different forms of behavior. And first of all, we have some easiest energy term, POTS, Hamiltonian. And why we use this form of energy with summation of all neighboring sites, and using the Kronecker symbol. It means that we should take into account only the surface energy between elementary sites of different cells, of different biologic cells. I mean, if we have sigma equals if we have in Kronecker symbol two same sigmas, we obtain that this energy equals 0. And sometimes researchers and models call this surface energy term. And we can rewrite this energy and make more complex using special multiplier. It's not the coefficient, but symmetric matrix of surface energies for different cell types. Tau is cell type. What is cell types in cellular post-modeling framework? It's different tissues which can meet in one computational domain. Up to 5 or maybe in some complex cases 6 cell types. For example, it can be tumor, epithelium, immune cells, like T cells, and for example, and of course, cellular matrix is medium. And then creators of this approach, Grenier and Glazier, which built this approach and formulated the main things, proposed how to account cell sizes, perimeter, and area of cell in two-dimensional case. We should we can include this term in quadratic form. Why in quadratic form? Because here we can see the difference between current, for example, area, and the target cell area. And using this form, we can govern the cell area. Or cell perimeter, which is very important to save to avoid cell fragmentation, for example, and we can make different energy terms more or less important using special Lagrange multiplier, doing it larger or less. And of course, we can use just well, okay, and don't forget about such important process like chemotaxis migration. And for this type of cell motion, more complex type of cell behavior, researchers implemented field of chemokines, and the difference of chemokines concentration is included in additional term for delta Hamiltonian. And this term was proposed for by bioinformatician Pauline Hogevec, and then cellular POTS model with other possible forms of Hamiltonians were called Grenier, Glazier, Hogevec model. Well, but how we can determine the direction of time evolution of the system? It's a very important question. For example, in thermodynamics, we also know the second law of thermodynamics, and in such complex systems like biologic systems described by sites or nodes united in biologic cells. It's more convenient to use some derivative law from second thermodynamics law. It's principle of least energy. For this purposes, we will use delta Hamiltonian after subtracted by Hamiltonian before. Well, on this principle of least energy have to be implemented into some algorithm which is very important on which have Monte Carlo structure. What will be the steps of this Monte Carlo approach? First of all, we should select some random candidate EG with coordinates EG with some sigma spin. Then we should select some random new value with spin with other spin sigma from Q possible values. And then is very important. Step 3, it was correction for step 2. To save time, we should check not from all possible sites with new spin, with other spin, but we should check only neighbors of this sigma site with EG coordinates. Just neighbors. I should underline this third step. Then we will calculate the new energy Hamiltonian after in the new configuration.
Ivan, excuse me to interrupt you. What is the meaning of spin here?
Yes, it's very helpful question. I should maybe make some explanation. The main thing that solar pods model origins from the beginning of 20th century and starts from numerical realization of Ising model. Ising model is used to describe important processes of magnetization in ferromagnetic materials, and this Ising in one D case and Anzager model in 2D case, in two-dimensional case. In these models, there are only two directions of magnetization direction, up and down of magnetic domains of microcrystals. Right, and this term spin originates from these models of magnetization. And then Jeffrey Potts proposed theory in which Q possible values were available with Q possible values of magnetization direction. And on other steps of abstraction, we come not to the some crystal structures, but to some biologic objects like cells, and I completely agree that spin, this word spin can a little bit maybe fits not very well, and I should explain that spin means one cell with its number. Each biologic cell have its own number, and here spin means only such number, and that's all.
But how this? I'm not sure to understand how this number is related to your problem. So what is the property? So as far as I understand, to each small square in your model, you associate some number which you call spin. Here, if you take a small square, like for example, small red square, so you say to each this small square, you associate some number. You call this number spin. But what is the meaning of what of this number? I mean, what is characterized? What property is characterized by this number?
I should explain that, of course, yes, we have some elementary squares sides, and each small side, elementary side, in different times can have different spins. How it could be? For example, this spin have, for example, number 2, because it's cell 2, it's biologic cell 2. But on the next Monte Carlo step, it will have spin which equals 1, because red cell change his shape and occupy, and this cell occupies this elementary site, and then observed site will have other spin value. Spin, of course, it's a little bit abstract quantity for when we consider some biologic objects, but in this model it means only what is the biologic cell.
Okay, so it is a characterization to which cell this small square belongs. Is it correct?
Yes, it's correct.
Okay,
yes,
so
correct.
whatever. So the word spin is a little bit confusing because spin is it has some particular meaning in physics. But anyway, it's some characterization. It is some characterization of the small squares, and in your particular case, it is to which cell the square belongs. If it is this, so you give this definition, it's okay. So please continue.
Okay. And when this elementary step of evolution, of system evolution occurs, we should recalculate the full energy system and obtain this Hamiltonian alpha. And then we will compare the delta Hamiltonian value, and to change or not to change the spin value to some new spin value. And what is the law of such time evolution. Of course, it's probability law. To be more appropriate and comfortable, the whole condition were divided on two cases. When temperature of system is larger than zero, if delta Hamiltonian is larger than zero, we should calculate the probability in such Boltzmann form with delta Hamiltonian and temperature.
No, excuse me. Again, what do you understand by temperature here? I suppose it's not just usual physical temperature, but something different. So please explain this.
You're absolutely right. I should, of course, explain. Grainer and Glazier and some of their colleagues in first papers used this term, use temperature without clear understanding what it could be. It was the end of 80s and beginning of 90s, because Glazier started from, for example, some processes in steels and in soap, right, in soap bubbles. Well, and for some precursors of cellular reports model, they use temperature and usual physical meaning. But next, when they translated this physical framework to some biologic processes, they wrote very helpful paper in 95th or 96th year. It was Glazier and maybe Mombach, and they used other experimental work using cytochalasin B, special inhibitor which affects proteins in cell membrane. And this inhibitor acting on cell membrane can stop any form on cell membrane fluctuations. And on microscope in vivo films, some movies, in chicken embryos, such cells looks like a little bit freezed without any additional motions, without any oscillations of cell membrane. Well, and in this case, not in this case, but this case of inhibition of membrane oscillations, we can correspond to zero temperature.
No, but you see, you give some historical background, but in your model, what you understand by temperature here, never mind what Glazier introduced 30 years ago, but what you understand here by temperature. Do you have some a random motion of these cells, and this temperature characterizes this random motion, or what? So my question is specifically about your model.
If you talk about the current model, well, it means very close processes of some stochastic oscillations of cell membranes, which allow us to make some energetically to realize some low probability configurations from energetical point of view using these oscillations of cell membrane. It's mean only this thing. Temperature is intensity of such oscillation and stochastic random fluctuations of membranes.
So, but let me understand. When you talk about probability of transition, you have two configurations, two consecutive configurations, the previous one and the next one. And this next one, you consider all possible transitions, and you choose between all possible new configurations. For these new configurations, you determine the value of Hamiltonian. So if the value of Hamiltonian becomes less, then you have this, as you write here, you have this transition with probability 1. But you can have many new configurations for which the Hamiltonian decreases. So what do I mean? You choose the minimal value of Hamiltonian, I mean the configuration with the minimal value of Hamiltonian?
No, it's some small feature in the beginning of this algorithm, which is called, I should, oh, right, it's modified metropolis algorithm, right? And the one feature is that first of all, we check one of q possible, we can say, configurations without taking into consideration this delta Hamiltonian. And then we calculate probability, especially for this new sigma configuration.
Yes, but if you have many, you consider all possible new configurations. For all possible new configurations, you determine the new value of Hamiltonian. For some of these new configurations, not for one, but for some of them, you can have the value of Hamiltonian less than it was before. So in each of these cases, for each of these new configurations, you have probability 1, but this is not possible to have for each of them probability 1. So this is what I don't understand. You can have several new configurations with the value of Hamiltonian less than it was before. How you choose between these several configurations?
It's just a random process of choosing one of configurations. Some of them can be associated with delta H larger than the 0, and of course it can be situations when the next configurations can be associated with delta H less than 0, but it's a random process. And for high temperatures, of course, the general trend during the very low temperatures is going to some local or global minima.
No, but sorry to insist, but I'd like to understand more precisely. For example, you have 10 new configurations for which the Hamiltonian decreases. Now you say this is a random process. The choice between these 10 configurations is a random process. But if it is a random process, you should determine the probability of transition to each of these 10 new configurations. So this is what I don't understand. You have 10 configurations with decreased Hamiltonian. How it's not sufficient to say it's a random process, it's a random choice, because you need to determine the probability of each of these transitions. You can say, for example, that it can be with transition to each of them can occur with equal probabilities. Or you can say that the probability of transition depends on the difference in the value of Hamiltonian or something else. But you should determine this, how it happens. You should specify your random process. Do you agree? Do you understand my question?
Yes, I understood. On this stage, all these possible next configurations are equal probability. But on this stage, when one of these next configurations are chosen, we should calculate this probability and realize or not to realize them next configuration.
Excuse me. Okay, let us really, sorry to insist, but suppose that you have not 10 but 2 new configurations such that delta H is less than 0. 2, only 2. So which of them you will choose?
It's one of these with equal probability.
So even, okay, now you say with equal probability. So you have the choice between 2 of them with equal probability independently of delta H, right? So even if for one of them the Hamiltonian is less than for another, it's not important. It's not important. It happens, this transition occurs with equal probability. So the choice between these 2 new configurations is with probability 50%.
Right.
Right.
Yes. Well, what I can say, this approach was introduced not only by Grenier or Glazier 30 years ago, and
no, excuse me, not important who did it before. I am just trying to understand what you say independently of the previous work. So this is what you say, just to understand. Okay, please continue. No, excuse me. So again, because what is confusion in these formulas you show on the screen, it's this probability 1. This is what is not clear, because it is not 1 in fact, but if you have 2 new configurations, so the probability between them will be 50%. So probability, say like 0.5. The choice between them. If there are 10 new configurations, then for each of them probability will be 0.1 and so on. And this is in the case for all configurations for which delta H is less than 0. But you can have also configurations for which delta H is larger than 0. And as you say, this transition can also occur with some probability which is smaller and which depends on some parameter which you call temperature. So this is what is a little bit confusing for me, because you have in fact if you have all these configurations, and if you count the total probability, it will not be 1, it will be a large number. So somehow we should divide this probability by the number of configurations. To have total probability, the sum of probabilities, you should have the sum of probabilities of all these transitions equal 1. The sum of probabilities.
Yes, you're absolutely right. In future, I will.
At least this is how I understand. It's the first part, and the second part, if the temperature, the second part temperature is 0, so no temperature. So what you write? If delta H is positive, so such transition cannot occur. You take probability 0. If delta H is 0, meaning that the Hamiltonian is the same, again, probability 0.5. But again, there are many, possibly there are many such configurations with the same Hamiltonian, or many such configurations for which delta H less than 0. So you should somehow divide by the number of such configurations. Otherwise, you have the total probability not 1, but larger than 1. So this is how I understand. Please confirm whether it is correct or not. And sorry to interrupt you. Please, you can continue.
No, it's not a problem. Yes, I should say that you're absolutely right. In this case, maybe I saw that for these conditions too much time that they are so usual for me, and maybe I have to watch them more with more higher accuracy, right? With more higher. I will rewrite, of course, these conditions to obtain more strict conditions, of course, for probabilities. I absolutely agree with you. With you, Nose. Thank you. Well, it's really a very important part of system evolution in this slide, and we can say that this slide is a cornerstone of all approach. Then some details about cellular pods modeling application areas. Well, first of all, we started from, and not we, but researchers 30 years ago started from modeling of embryogenesis and cell cycle of such modeling objects like bacteria and I forget how it will be in English. Special organisms. Okay.
You can say it in Russian if you
грибы-слизневики, которые могут активно двигаться.
Well, okay, I understand, but I don't remember.
I forget the name, sorry me. And then it's also very important area, maybe most helpful and most important, right? It was such areas like wounds healing using fibroblast cell and immune cells. It was also descriptions of cell motility, like today's work, using chemotaxis, hepatotaxis, amoeboid motion. Of course, it's naive T-cell activation in lymph nodes from work of Netherlands School of Cellular Pods Modeling. It were some models of T-cell epidermis patrolling. And of course, it works about CTL, cytotoxic lymphocyte activity of immune cells against tumors. Then, of course, if you talk about some application to oncology diseases, CPM also can help when we describe invasive cancer behavior, tumor growth in form of, for example, 3D spheroids, tumor vascularization, and it was a long list of such works. And at the end, it was also very complex for me works about describing of bacteria behavior, like bacteria accumulation in tumors, bacteria films, thin layers, and very complex swarming behavior of segmented bacteria. Well, it is very wide spectrum, but of course it's not the whole list of applications. And before I will go through my input using this approach, I should answer which tools we can use for calculations. Some of first and I suppose main tools was built by James Glazier. It was some of creators of the approach, some of two creators. Then maybe most convenient tool was made by German researchers, Johann Strauss, Walter Diebeck, Lutz Brüsch, and Andreas Deutsch. And maybe the last very important tool implemented in usual browsers was created by Netherlands school, Inge Wortel, Ioana Niculescu, and their lead, Johannes Texter. This approach was written by in JavaScript framework, and it was very difficult to me to implement in this tool, artificial tissue toolbox.
Yes, excuse me, Ivan. How much time do you need more for your presentation? Because normally our time is finished. So if you still have several minutes, we can continue. But if you need more time, maybe we can think about to continue some other time. So please, how much time do you need for your presentation now?
Well, I don't have the watches on my hand. And
how many slides you do have?
I have enough slides. Maybe I need maybe half of our.
Then I would suggest, if you don't mind, to continue the next time, because it would be really interesting to discuss and to listen what you present, and in particular these software tools, and if you can, for example, show these software tools how to use them. I think it would be interesting and useful. So in this case, what do you think? Can we stop now and continue the next time?
Yes, I can stop now and continue in other appropriate for you and for audience. Of course.
Yes, Anastasia, what do you think about this suggestion?
Yes, okay. The next open date we have, it is February 22. Is it convenient? 22, February 22.
Yes, на следующей неделе я помню, и что, все остальные там у нас тоже заняты, да?
Так, у нас занято 1, 8 и 15, да.
Уже занято, да? Хорошо, Иван, что вы скажете по поводу 22 февраля?
22 февраля, мне кажется, будет замечательно.
Что?
Я согласен, да. Да, абсолютно согласен.
Хорошо, давайте тогда, потому что не хотелось бы комкать сейчас ваше выступление, потому что мы уже больше часа продолжается наш семинар, но обычно у нас час продолжается. Ну, просто я еще прерывал вас вопросами и так далее. Вот, поэтому, чтобы не комкать, может быть, да, перенесем тогда сделаем вторую часть. Это совершенно нормально, мы иногда так делаем. И было бы также интересно, я не знаю, вы предполагали это показать или нет, было бы также интересно, если бы вы показали вот эти вот, ну, не обязательно, может быть, все вот эти комплексы программ, может быть, вот то, что вы используете, так немножко, чтобы мы познакомились тоже, как этим пользоваться, как это выглядит и так далее. Хорошо?
Да, конечно, да, я, конечно, извиняюсь, что немножко не рассчитался со временем.
Ничего страшного, наоборот, мы с удовольствием вас послушаем, продолжение доклада в следующий раз.
3 из этих инструментов я, конечно, смогу показать.
Ну, хотя бы один, ну, на ваше усмотрение, но хотя бы один, потому что для наших вот слушателей это тоже может быть полезно. Во-первых, познакомиться с этим программным обеспечением, может даже использовать. Поэтому, пожалуйста. Well, so I will summarize our discussion. So we decided to stop this first part of the presentation now and to continue with the second part of Ivan's presentation the next time. The next time will be on February 22, so more or less in 1 month, because we have already our seminars planned. Next several seminars are already planned. I also asked Ivan to show and to explain a little bit about the software in such a way that our listeners can eventually in future also use the software, because this is useful for many different biological problems. So please ask the questions now about this first part of the presentation.
I have small question, if I can.
Please, Anastasia.
My question about the structures which you explain and which you would like to model the moving of cell on it. Does they present only in lymph nodes or in other parts of the organism? They can only be present. Reticular network or fibroblast network.
Well, I can answer you without any slides, maybe, or using just words. Well, as I know, such a reticular fibroblast network, the main place where we can meet such structures is, of course, lymph nodes and T cell zone in lymph nodes, because in other parts of lymph nodes it will be other structures. However,
so there is no such structures in the interstitial space, for example.
Right, it can be very close structures. You're right. I mean, it can be a little bit. It can be small difference, because special structures of a fibroblast reticular network causes from special need to be like tubes for for antigens, and the fibroblast like cells, not like collagen structures, should also emit special chemokines to control motility of immune cells, and maybe in other, for example, like in other tissues like joints or epidermis, we can meet similar but little bit simplified structures without any important details.
I would also add that it depends what particular biological physiological process we consider. If we talk about the interaction between lymphocytes and dendritic cells, for example, I suppose that it occurs mainly probably in lymph nodes, but there are many other probably biological or physiological processes where fibroblasts and fibroblast networks participate. So in this case, it might be not only lymph nodes, but some other organs and tissues.
Thank you. And of course, when immune cells became activated and come to the next stage of effector cells and CTL and for example, effector and CTL stage, they can use similar structures like fibroblast networks in other places. For example, in epidermis, in tumors, for example, because we know that tumors also consist from extracellular matrix, neoplastic cells, and immune cells. And even in tumors, we know we can meet special lymph node-like structures. I remember they called tertiary lymphoid structures, which are placed in tumors, but very close or very similar on lymph nodes, because there are very much immune cells here.
So this is
very interesting. I didn't know about this. Thank you.
Yes, indeed, I'd like to continue with this point because indeed it is interesting, and I'd like to understand better what you say, that when already mature lymphocytes, like for example CTLs, come to the target tissue, to the infected tissue, for example, to the epithelial tissue, for example, do you mean that there also they can use these networks for their motion?
Well, I mean the main part of way they use our usual blood vessels.
No. This is clear that they're transported there by just blood circulation. But when they come already to the tissue, inside infected tissue, for example, we have this whatever influenza, COVID, whatever, this infected epithelial tissue. So these CTL lymphocytes come to this tissue. Inside the tissue, what happens? Do they move also due to, because you mentioned chemotaxis, so probably in the lymph node, lymphocytes move partially due to their random motion, and partially, as you say, you confirm or not, partially due to chemotaxis, right, in the lymph node. But when they come to the infected tissue, for example, epithelial tissue, what kind of motions they have? Do they move there, like independently? I mean, not transported by blood, but do they have their own motion there? I'm talking about lymphocytes. And if they can move, what is this motion? Is this a random motion or directed motion due to chemotaxis, or the motion according to fibroblast networks?
Well, when immune cells are already in infected region, they also can use similar possible structures. But sorry me, because I'm not completely informated about some processes connected with virus or bacterial infection. But of course, T cells can use fibroblast reticular networks in other places. For example, it can be even not the such highly organized structures like this highway roads fibroblast network. It can be just filaments of this tissue. I mean, simple fibers of, for example, collagen and fibrin, not big, not the large rods, but small fibers, small separate fibers. And in such cases, the velocity will be lower. The persistence of such motion will be also lower. However, of course, and this is many times confirmed fact that in human body there is a very high role plays special inflammation cytokines like interleukin-6, interleukin-2, TNF alpha, and I'm not sure, but I suppose that these cytokines can attract these inflammatory cytokines can attract immune cells to this inflamed region.
Yes, this is something we discuss quite often, but it's a little bit different. So this is why I ask about that. So we know that inflammatory cytokines, interleukins in particular, and some other inflammatory cytokines, indeed they determine the influx of immune cells in the inflamed tissue, and it can be in the case of viral infection, or it can be in the case of atherosclerosis, but the mechanism is different. In fact, the mechanism is related to the activation of endothelial or epithelial cells. And so if we consider endothelial cells, so if we consider a blood vessel, so there are endothelial cells which separate blood vessel from the vessel wall. These inflammatory cytokines activate this endothelial cell. So at the surface of this endothelial cells, there are receptors which are activated, and then these white blood cells, they roll on the surface of this blood vessel from the side of the blood flow, and then they come to this activated place, to this activated receptors, they stop there and they penetrate inside the tissue. This is how it happens. And it happens both for monocytes, which become later macrophages, and also for lymphocytes. But my question was more about when they are already inside the tissue. We know that macrophages, and this is of course very important, that monocytes and macrophages, they move inside the tissue due to chemotaxis. This is a very important mechanism. But I don't know about lymphocytes, whether these lymphocytes move, whether they can really move, whether they move due to chemotaxis, or they have random motion. This was in fact my question. But I understand that it's not a simple question. So if you know, you can tell us this time or the next time. If not, we will think about that. Okay, so if there are no other questions, so thank you again, Ivan, for this presentation. It was very interesting because, you know, I know this. I'm a little bit familiar with the cell pods models. I never used it myself in my work, but just I know something about that. We used more off-lattice models in such biological problems where we model cells moving not in the lattice, but you understand, like a soft sphere model where it moves, where the soft sphere moves as well, like for example, the center of this sphere can move according to the Newton's second law, right? So it can move like that due to the forces acting on this cell or on this sphere from other cells around. So okay. Anyway, so I'm more familiar with such approaches, but also I know a little bit about the cell pods model. So this is indeed very interesting, and I also hope that our listeners who might be less familiar with that they now know something about that. And we look forward, Ivan, for the next presentation where you will explain us how to use these different softwares and about your own results. Thank you very much. We finish our today's seminar. Have a good day. Goodbye.
Thank you, Vitaly, for invitation. Goodbye.
Thank you very much. Goodbye.
Anastasia, you will announce, right? You will announce the second part.
Yes, I have already updated the schedule on our site, and the announcement will be later, about maybe a week before your second part.
Okay, thanks. Bye to everybody.
Bye.
Bye. Thank you.
Goodbye.
Thank you. Bye.